Hello, Math 8 students. This is Open Up Resources, Unit 1, Lesson 13 on congruence. We're going to start with this activity. It works as a great warm-up. So I'm going to ask online learners to pause the video long enough to give them a chance to answer these first 3 bullet points here. We are looking for corresponding points and labeling them to show that they are corresponding. And then you're going to be asked to label 3 of your own. So pause the video until you have that done. And now that we're back, I need one student to go up and show me where E prime is going to be in the new figure, because it says to label the points E and F in that new figure. So where would they be? Lucas, go show me where E is. And then Cole, will you show me where F is going to be? Make sure you guys remember to sanitize your hands when you return to your seat. Will you click over on the edge where it shows the highlighter? So tap on the screen again. Oh, it looks like it'll work for you now. It'll be a pen now. Oh, careful, it's not F though, Cole. What is it going to be called? F prime. There you go. And see if you can label that one for us now, Lucas, if it'll work. E prime. Beautiful. Okay, now what about G8 or G prime and H prime? Where would those be in the original figure? Tyson and Callista. All right, Tyson, what is that point going to be called? Maybe look at your paper. Okay, and I noticed that Callista just labeled it H instead of H prime. Why did she label it H instead of H prime? Nadia? Exactly. We're labeling the original, not the new one. And Tyson labeled it G instead of G prime because it's G in the original figure and G prime is in the image. Very nicely done. So now I need 3 more students to do what the next set of directions says. It says label at least 3 more pairs of corresponding points. And you can label them anything you want except for these letters that have already been used. You'll have to pick different letters than what has been used. Landis, you can go and do 1 pair. I need a couple more volunteers. Garrett, and I've already heard from Cole and Lucas. I need someone new. Xander. Good, I like that point. What are we going to call it, Landis? Sure, you can call it I. I and I prime. Good. That one works. Looks like that's an L prime, right, Garrett? Okay, good. Uh-oh, what should we call this one? If this one is P, what should this one be called? P prime. Very good. Okay. I'm just going to move this G since it was kind of covering up point L. Everything looks great. Who had a different point? Is there a different point that somebody used? Landis, what other point? Don't go on up there, but can you describe it? Yeah. Yep, so we could have also chosen this one. Oh, this one? Right here? This one? Oh, that's weird, but yeah, that would work. Could I do this one though? Yeah? I would call that one maybe X prime and X. I like that, Landis, you're getting to exactly where I wanted to start thinking about is all of these other points that were chosen before all had at least some sort of crosshairs, right? They're not on the edge, they're not on a vertex, but they're still like at a very defined point. But I like that you're branching out from that and you're saying we could even go in the middle of nowhere, like Z, and we would call this one Z prime. So now my question to you is this. What if I wanted to be even more different and I wanted to pick exactly Oh, and let me do a color that you can actually see. What if I wanted to pick exactly this point? How are you going to know exactly where that point is on the other figure? I'm going to call that one S. Where would S prime be? How can you figure it out exactly? Discuss with your groups. How do we make sure it's exactly perfectly where it needs to be? Talk to each other. 15 seconds, go. Garrett, that's not your group. Your group is waiting for you to talk to her. Time's up. What should we do to make sure that we get S prime exactly where it needs to go? What would you do, Parker? You could measure it and use tracing paper. And I like the tracing paper idea even better. So, if you haven't already done this, get out your tracing paper and trace this figure on your tracing paper. And pick a spot that is about where my point S is going to be. Make sure that you have that. Maybe even poke a hole through that point S. And here's the lovely thing about tracing paper. We already know that these figures are congruent. It already said that they are congruent. So that means when I trace this and I translate it to the right, all of those points line up, and now I know exactly where S prime is going to be because I poked my hole through the tracing paper, and now I can draw on the paper below it and call that one S prime, right? So that tracing paper, helping us with our rigid transformations, is really, really helpful for identifying some of those corresponding points. And then we had a challenge question that I left you guys to deal with. Super fun. We used 12 toothpicks here to create a polygon, and the polygon had 5 square units for the area. So, can you use the same 12 toothpicks and created a polygon with an area of 4 square toothpicks? Let me warn you before I get a bunch of people saying, yeah, I can do it, and this is what it looks like. This doesn't count, because this is what my first period tried to get away with. They did 1, 2, and pretend like those are all touching, but they're toothpicks, so I'm kind of separating them so that you can see the difference between them. Does that make sense? So 1, 2, 3, 4 toothpicks, 5, 6, 7, 8 toothpicks. Is that an area of 4 square units? Yeah. How many toothpicks did I use? So like, oh, I'll just randomly put some in the middle. That's not going to count because that's not forming the polygon. That's just kind of separating the polygon. So that wouldn't work. How can I actually form a polygon that has 12 pieces forming the polygon and still have an area of 4 square units? Was anyone successful? Yeah, you can't use the one that's already there. Anyone? All right, let me show you the one that, because this one hurt my brain a lot too. And if I'm being perfectly honest, I had to look at the answer key to get some ideas. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Have I used all 12 toothpicks? No. But do I have an area of 4 square units? Watch what I'm going to do then. Instead of using 1 toothpick here, what if I use 1 and 1 to jut it out? Have I used enough toothpicks yet? I need 1 more. So instead of using a toothpick here, 1 and 2. 1, 2, 3, and then where's the 4th? Here and here. I got that from the answer key. That's totally not my own. It hurt my brain way too much to try and figure that one out. Okay. Is your brain working now, though? Wrong answer. Is your brain working now? Did you learn something? Okay. Let's move on to the next exercise then. It says, we're looking at congruent ovals now. So I want to take from what we did at the very beginning, that very, very first warm-up piece, right here. And normally we have labeled points and talked about points that are on the vertices or the multiple vertex, right? So we're always looking at the corners. I'll wait. Where should your attention be? Thank you. We've always paid attention to the points that are on the vertices. But with this warm-up, we also identified that we can still find corresponding points that aren't on the vertices, like this point and that point, and this one and this one. And even this random one that's kind of hard to see exactly where it is, but we've still found the exact corresponding point there too, right? So we're going to take that concept and take that idea to now asking this question, are any of these ovals congruent to one another? There's not nice vertices, right? We're dealing with ovals now instead of polygons. But can we still figure out if they are congruent? Work with your groups. I'm going to keep this recording going. I'm not going to pause it. So online learners, you have all of this time to also work through it and figure out, are any of these ovals congruent? What tools are you using as you're answering this question? Tracing paper might be a good tool to use. Ladies. Put those away, please. Thank you.
Okay. At least that's what I think.
Okay, did we find any that were congruent? Which ones did you find, Mason? The two top are congruent. Do you guys agree or disagree? Okay, so I'm going to shade them the same color to show that they are congruent. But how did you guys know that they were congruent? What did you do to show that they were congruent? Lucas? Okay, good. I love the use of the tools. I'm trying to do the same thing. I am not so good at this tracing thing. I hope that you guys were a little bit better than I am. But we could use our tracing paper, right? And we could move it, you said, but how specifically am I moving it? Zeta? You have it, sorry? A rotation, exactly. I'm rotating it. How much am I rotating it? 90 degrees. And then a translation. Or we could find a specific point. Maybe you guys found it, maybe not. But yes, this is a rotation, 90 degrees. Which direction? Clockwise. Yeah, actually, no, it wouldn't have mattered. You're right. But still, since I did it clockwise, I want to be precise and specific, okay? Yes, Mason? Okay, we'll get there in just a second. You're absolutely right. We'll get there in just a second. Landis, you have a comment? Zeta? Okay, you counted the area too, tying into our previous lessons, right? However, I do want to point out, isn't counting the area of this a little bit more difficult? Because we don't have whole complete squares like we did before, right? So I do kind of like that idea of one thing that was mentioned in a previous class is even though they couldn't find the exact area of the oval, they kind of made a rectangle to go around it. And then that rectangle that goes around it, it has the same area as this rectangle. And that's not going to be 100% precise all the time, but I think it's at least a good way to get us started in our thinking process, right? Okay, so here's what I want to take away from this so far. You guys all used your tracing paper to show that they're congruent by doing a rigid transformation. So we're going to write that down because this is still really important. This is a big takeaway from the whole lesson. We can always show congruence. Sorry, not by, through. We can always show congruence through rigid transformations. This is the most effective method because the definition of congruence relies on rigid transformations. So if we ever want to say, is it congruent, we can rely on that definition. As long as you can find a series of rigid transformations, you're going to be good to go. And using that same concept, we'll hit on what Mason said too. Mason earlier said we can also see that this oval is congruent to this oval. So I'm also color coding those. Is this yellow one congruent to this cyan one? No. You tried it? And it doesn't work, does it? So that's the other takeaway. Okay? Kind of going back to what we did in the very beginning with finding these multiple points, right? Focusing on points that aren't always on the corners, just like this. This doesn't have any corners, so what points could I look at? Why don't we look at this point and this point? How long is it from this point to this point? 3 units. I'm going to write that down. What are the corresponding points in this figure? Knowing that it's been rotated, we would see that this point would correspond to this one, and this one corresponds to that rotation right there. And what is the distance between those same corresponding points? We're not surprised by that, are we? That makes sense. So, to go back to my earlier point, I asked, is this oval, yellow, congruent to this oval, cyan? And you said, no, it's not. How do you know? Instead of having to use your tracing paper, I want to focus on this distance here. This is 3 units. Oops. Is this 3 units? Do I even need to know how many units it is? No. Is it the same as it was here? No. And that's enough. This is not the same distance. So I know that they are not congruent. Oops. That's also an important thing to summarize. You may not realize it yet, but it is important. So I'm actually going to do that one in purple because I'm going to use the same color purple to color code something else later. If you are trying to color code notes with me, I'm writing here not the same distance. So what I'm going to be writing is this. We can also use distance between corresponding points. Thank you all for writing this down and including it in your notes. I'm going to pause here. Give everyone enough time to get caught up because I'm going to make a really important point. Want to make sure that you're listening. Okay, eyes on the screen. Before, I said we can always show congruence through rigid transformations. Okay, we're showing or proving congruence through rigid transformations. But here, I'm going to write something different. We can also use distance between corresponding points, not to prove congruence, but to give us clues. That's important difference to note. To give us clues about congruence. Finish writing that. So what is the best way to show congruence all the time? Through rigid transformations. If we don't always want to go with the rigid transformations route, we can get clues. It's not going to prove congruence, but it will give us clues about congruence. With that in mind, we're ready for the next exercise. Again, I'll kind of walk you through some of those first steps that I'm going to let you guys discuss with your groups. It says, draw the points corresponding to B, D, and E, label them B prime, D prime, E prime, because these are already congruent shapes. It tells us that in the directions. They're already congruent. So we need to label the figure. Where is point B going to be? Label it on your paper. Sorry, I misspoke. Where is B prime going to be? Put it on your paper. Where is D prime going to be? Put it on your paper. Where is E prime? Put it on your paper. Did I get them in the right spots? Did you get them in the right spots too? Okay. If you feel the need to add F, you can. Well, where do you think it would be? A, B, C, D, E. Yeah, if you go around, you can see kind of where it probably should be. It says draw line segments AD and A prime, D prime. So I'm going to do that. Here's A to D and A prime to D prime. And we'll continue with a few other points, but it says, and measure them. So measure AD, measure A prime, D prime. Measure them, that would be what we do with our index card. See if they're the same length, see if they're different lengths, and continue that for each one of these other pieces, BC and B prime, C prime, AE and A prime, E prime. Get those lines drawn and measure them. I will give you guys about 60 seconds while I do it on the video. But you guys need to be doing it and measuring them, discussing with your groups. Does that mean you're noticing some important things? I should be hearing group discussion at this point. You should be done getting those lines drawn, and you should be measuring them and talking about the measurements that you're seeing. Discuss, please. All right, I'm not going to keep wasting time. You guys are refusing to discuss. I'm moving on. What did you notice? Thank you. For the one student.
Sure I understand.
I'm not talking to you, Siri. Yes, thank you to the one student who actually did the activity and measured them. What did you notice, Landis? They're all the same. All the same? So CB is the same as AE?
No, like the primes are the same. So CB
CB.
is the same as C. But B prime and C prime.
Okay. Yeah, so C prime B prime is the same, sorry. C prime B prime is the same as CB, right? So the originals are the same as the images. Okay, that's kind of a big deal. Let's write that down. I feel like that's kind of the whole purpose of this activity. What do you notice? The lengths are the same. It is a reflection, you're right. Rotation a little bit, or translation a little bit. Translation and then reflection, or rotation and then reflection. The lengths are the same. So, with that in mind, my question to you is this. Do you think there could be a pair of corresponding segments with different lengths? Could I create a segment in this figure that would be different than the corresponding segment here? Discuss that question. I actually want there to be actual discussion, actual student voices talking to each other. Could it possibly be different ever?
Possibly. It could just be like, it's barely different, but it could still be different. But if it's bigger, then it's not corresponding.
And time's up. What do you think? Could it possibly be different? I want to see the hands. Not enough hands. Thank you. Garrett?
I don't think so because if it's the same shape, then it would usually have to stay about like the same length unless it was like so say B prime and B prime, unless B prime or B prime were like moved in a different spot and the other one was the same that it is now, then I guess it could.
Okay, and if we did that, if we made those moves like you're suggesting, if B was in a different place, then are those figures congruent anymore? No. So if the figures are going to be congruent, what about all of those distances? They're going to also have to be congruent. They're going to have to be the same, right? So no, if they are the same shape, meaning congruent shapes. Thank you for writing this down, including it in your notes. Then the distances are also always going to be the same. As a matter of fact, when we very first started talking about rigid transformations, that's exactly how we defined it. We realized that in rigid transformations, the angle measures stay the same and distances. We didn't even say side lengths back then. We actually said distances. And I said distances like side lengths. So we've already known this. It's already been part of that definition of rigid transformations. It's just something that's going to become really important now as we're having figures that don't have straight sides anymore. So something that I would like to point out is keep in mind that as we're doing these transformations, we're modeling all of them with tracing paper, right? So once you trace something onto your paper, and I'm going to try and do a bad job of this. I'm actually trying to do a good job, but it's turning out to not be perfect. Okay. So when I trace this onto tracing paper, and if all I'm doing is just spinning that tracing paper around or just flipping it over, is it going to change what I already drew on the paper? Is it going to make it longer or shorter as I'm just spinning it around or moving it? Exactly. So it makes sense that this, I'm going to try and group some of these together. It's not liking it. Let me try that. Okay, so it makes sense that as I've drawn this, and I even drew that segment that kind of connects those pieces, and if all I'm going to do, I actually have to reflect it, huh? So flip, we'll go left, right, and then I'll rotate it into position. Notice that I'm not changing the size, I'm just kind of moving that tracing paper, so is anything going to be changing in size or in that distance? No, it's pretty intuitive when you actually think about, I've already physically done it on the tracing paper and I'm just moving the tracing paper. So it really does make sense. Now, with all of that in mind then, we have this challenge where if we really wanted to prove congruence by doing these corresponding points, I'm going to come back to this example here. I have the challenge of needing to show every single distance is congruent. Here's what I mean by that. We showed that this was congruent, right? That was easy. And maybe this one would be easy too, because that's how tall is the figure? You guys can count out how tall is the figure. Thank you. And so how wide is this one? 2 units. But we have to prove every other piece, like this one that goes from here to here, and this one that goes from here to here, and this one that goes from here to here, and this one that went from here to here, and then here to here. And do you really want to measure every single possible distance just to show that they're the same? No, it's a very daunting, impossible task. And so that's why I want you to understand what we wrote in purple, that we can just use that corresponding distance to give us clues. Just like this distance here gave us a clue that yellow and cyan were not congruent. But we don't want to have to go through that process and prove every single length is the same. It would be too tedious. So the best way to still prove congruence is with that rigid transformation. With that in mind, we have Max and Frankie. These are the faces of Max and Frankie. Are these faces congruent? I'm only going to give you guys 30 to 60 seconds to talk with your groups and figure that out. Are these faces congruent? Ready, set, go. Make sure you prove it.
Yeah, with white too.
Yeah, so the circle around the
Okay, time's up. Raise your hand if you say yes, Max and Frankie are congruent. Raise your hand if you say no, Max and Frankie are not congruent. Everyone's raising their hand for not congruent, and you're all wrong. I'm going to prove it to you. Watch this. Look at the eyes. I'm going from this distance to this distance. And isn't that exactly the same as this? Yeah, so they're congruent, obviously. And even this eye, it's that wide, and this eye is the same width. So obviously they're congruent, right?
No.
Why are you still saying no? I just proved it to you. Let me show you with the face. Watch. Look at that smile. And same thing. How have I not convinced you that they're congruent? Obviously they are. Nadia. Exactly. So I was making a false statement, and I tried tricking you guys, but you guys are too strong-headed, and that's okay. Is this eye congruent to this eye? Try that again. Is this eye congruent to this eye? Yes. However, are the whole faces congruent? No, because we need to look at the distances between all of those things, and this is the easiest way to show that. What's the distance between the eyes? Well, that amount, right? We can't really explain it. Probably 1. Yeah, it looks like it's 1. So if they were congruent, how far apart should those eyes be here? 1. And are they? No. So are pieces within that face congruent? And the face shapes themselves, are those face shapes themselves congruent? Are the face shapes themselves, just the shape, not the whole, but like, is that congruent? Yeah, probably. Oops, probably. But are the actual faces themselves congruent? No, they're not. Yeah, the mouth actually didn't move. Maybe it moved down. I think it also rotated a little bit. Yeah.
When you moved the line,
yeah. You saw it? No, these are not congruent. And I want to be specific and detailed here. And I want to say, even though the pieces in the face are congruent, I'll even say even though corresponding pieces of the face are congruent, the key thing is, and we're writing this down, all of the distances have to be congruent, including the distances between the pieces, right? Let's see. All distances would need to be the same too. And they're not. Okay. Below this exercise, you guys do have the cool down. I'm going to skip the cool down for a second. I want to go back to the summary. We're going to summarize first, and then we'll go and do the cool down. So I'm going to highlight, and I'm going to underline in purple that same piece of information that we had in purple earlier too. To show two figures are congruent, you align one figure with the other through rigid transformations. We've said that multiple times, almost every single lesson we're continuing to hit on that. If we want to show congruence, we have to do it through rigid transformations. It's true even for figures with curved sides. Distances between corresponding points on congruent figures are always equal, even for curved shapes. And it's just saying, for example, we have this distance AB is the same distance as A prime B prime. Trace it on your tracing paper. It's just been rotated. And here's the part that we need to underline in purple. I'm going to highlight it and underline it in purple because I want to get that color coding. To show that two figures are not congruent. You can find parts of the figure that should correspond, but have different measurements. That's what we also wrote in purple earlier. It's a clue. It's a tool to help us show that it is not congruent. For example, these two ovals don't look congruent. On both of them, the longest distance is 5 across. Okay, so we do see that it's 5 across on both. That's great. We can also see that they are 4 tall. This one is 4 tall. At its tallest point, this one is also 4 tall. Do you see that? However, look at where that's happening. This is happening smack dab in the middle. Where's this one happening? Not smack dab in the middle, right? So that distance is not preserved. Yep, it should be here, but it's not. It happens there. Okay, and now to our cool down. Let's finish that up.
Oh, that's back.
Then you haven't followed directions if you already completed it. Are figures A and B congruent? I want you to pay attention to what we highlighted here in yellow. To show two figures are not congruent, you can find parts of the figures that should correspond but have different measurements. So it's just that simple. How long is figure A? It's that long. Is it the same length in figure B?
No.
Definitely not. It's just that simple, right?
Yeah, B is 4. A is maybe 3.
It looks like 3. Okay, your homework. Lesson 13, practice problems. Get those done. That's it for today. We'll see you next time.